back in the New York groove. Ace Frehley, Kiss. Check it out. It's a good song. Now we're ready for Dalton's Law. Dalton's Law of partial pressure. On the sheet, there are two Dalton's Law problems. Two. Okay, let's go through them. Dalton's Law, I call it the gas law. Hello. Now, what I mean by that is, it should just make sense. It's like so easy, even a cave person can do it, okay? Let's be inclusive, people. Now, let me give you an example of Dalton's Law. Dalton's Law, so we've got two containers. Okay? Equal volumes. This container here has 5 particles of gas A. Green. The green will equal gas A. Gas B. Blue. Now this container over here has 5 particles of gas B. Okay. Pretty simple so far. That's it? No, that's not it. Just wait. We were to get a pressure reading on this container here. Now let's make a number up. Maybe the gas pressure is 1 atmosphere. 1 ATM. Okay? 1 ATM. This one here, these are next to each other in a lab, so they're the same pressure, same temperature conditions. So therefore, this one must have 1 atmosphere as well, pressure. Now I say, why does this one also have to have 1 atmosphere? Because look at how many particles they have. Equal particles, same temperature, you get the same room, same volume. So we both would have a 1 atmosphere pressure that they're exerting on their container. What if I decided to take the lid off the first container? Take the gas, take the lid off the second container, and dump it in. This works great. Try it at home. Not for professionals only. Okay. So we take these gas particles and we now mix them 3, 4, 5 with the gas particles in the other container. Now this container has 10 gas particles. What will the pressure be? What will the pressure in that container be? Come on, you know the answer. You do. It's logical. If this was 1 atmosphere with 5 and this was 1 atmosphere with 5, I took the two and combined them together. Now they have 10 particles. Same container, same temperature. Should be 2 atmospheres. Now, also, so now we have a 2 atmospheric pressure inside this container, but also what we have is we have a pressure due in part to gas A and in part to gas B. That means the partial pressure, the pressure due in part to gas A is 1 atmosphere and the pressure due to gas B is 1 atmosphere. Those two partial pressures total the total pressure of 2 atmospheres. In a real fundamental way, that's what Dalton's Law of partial pressure says. It says the partial pressures of each individual gas in a mixture of gases they combine all the partial pressures to make a total pressure. Or another way of saying it is the total pressure in a container is due to the partial pressures of each individual gas. Makes sense? Okay. All right. Let's do some problems with that. Okay. So let's see. Take a look at the first problem. Okay. Got your sheet right? Good. Good for you. A mixture of helium and argon are collected over water. Why did they tell me that? At 30 degrees Celsius and 775 millimeters of mercury pressure. That's pretty much close to average air pressure. Close. If the partial pressure of the helium is 430, what is the partial pressure of the argon? So let's see, we've got helium and argon in a container. Now it's being collected over water. So what does it mean being collected over water? Well, let's actually take our container and make a flask out of it. If we were in class, which we're not, you would do this in lab. That's a flask. Not a very good flask, but quit being so judgy. You would take an empty container. You would place that empty container in a container of water. You would have a reaction. Here's a test tube, and it's got a thingy and a thingy coming out, and it's got a thingy coming in here. Got lots of thingies. Reaction makes some gas. That's a test tube, that's a stopper. That's a glass elbow, and that's a piece of tubing. You see it, right? Thank you. Good drawer. Gas goes. Now you filled this container with water before you put it in to this container of water. So this is filled with water. What's going to happen is the bubbling of the gas, bloop, 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 is going to displace the water. As more gas is produced, the water in the flask gets displaced, and they're called volumetric flasks, so they have readings on them. You can read the volume in the flask. So let's say the reaction stops and the water level is going down from the top to here. You can take that reading of the volume and determine how much gas you've collected. So you collect gases over water because you know how much volume you collected. Now that was giving you some background on why it said collected over water. So that's going to do something. When you collect gas over water, because it's collected over water, there will be some water vapor particles left over in the volume of gas that you collected. So in this case, we've got argon. What was the other one? Helium? Helium, I think it was helium. Yeah, argon, helium, and you're going to have a little bit of water vapor because you collected it over water. So those three gases will be together in a container that you're collecting the gases in. So let's get rid of this. Okay, so now let's draw the container. You've got helium. You've got argon. And you'll have a little bit of water vapor. Moving around the container. So the pressure is caused by all three of those gases, the argon, the helium, and that little bit of water vapor because you collected it over water. So that means, now I was told in this problem, I was told that the gases are collected over water at 775 millimeters of mercury. Now the reason we're told that is because the gas pressure on the inside will equilibrate to the pressure on the outside. So collected over water at 775, that means the gases themselves will have a pressure of 775 millimeters of mercury total. So the total pressure, PT, is 775 millimeters of mercury. You were also told that the pressure of the helium is 430. So I know the helium is 430. I know that the water vapor is, oh look, vapor pressure of water at 30 degrees, and we're collecting at 30 degrees. That'd be hot. It'd be like Africa hot at the equator in the summertime hot. 31.8 millimeters of mercury. So that means you, water vapor, are contributing 31.8 millimeters of the total pressure. The helium is contributing 430 millimeters of the total pressure. So, the argon, how much pressure would it be contributing to the total amount of pressure? It's a relatively straightforward problem. You take the 750, 775. My bad, Joe. 775 and subtract 430 and also subtract 31.8. So you might say, well, why did you just add it? You said subtract. Well, I'm just taking these two together, combined. We're going to subtract those from the 775. And when we do that, we will come out with how much pressure the argon must be contributing. Because remember, Dalton's law is like, well, duh. If this is your total, And this is part of the total and part of the total. If we subtract those two parts, we get the remaining part of the total. And if I take this and subtract it, that's 461 minus 775 minus 461 should be a little bit over 300. So if we look at the answer, yeah, a little over 300. 313.2 millimeters of mercury. See if you get that. Subtract those from that. Should get 313.2. All right? Okay. First gas law problem with Dalton's. Let's try another one. Second gas law problem, using Dalton's law, is water is completely decomposed into hydrogen and oxygen. Water is decomposed. Decomposition reaction, we all remember those. So let's put those. Decomposition reaction. So our water is going to decompose into hydrogen and oxygen. Let's make it a balanced equation. Balance our equations. Okay. All right. Sweet. What's the question even asked? Let's find out. Okay. The total pressure of the gases is 700 millimeters of mercury. What are the partial pressures of the hydrogen and oxygen? So this question is saying that these gases together, when this water breaks down, ends up being a total pressure of the hydrogen and oxygen of 700. How much of the 700 does the hydrogen contribute? How much of the 700 does the oxygen contribute? Well, how am I supposed to know that? I ain't got anything else in the problem. Here's what you know. 2 hydrogens, 1 oxygen. If I were to draw that out in a container, 2 hydrogens, 1 oxygen. That's it. Those are moving around hitting the container. Who's causing more pressure? The hydrogen. Why? Because there are 2 of them. We have twice as many collisions with the walls of the container with the hydrogen than you do the oxygen. So therefore, the hydrogen produces twice the pressure that the oxygen does. It is that simple. So, but you might be saying, well, hydrogen's a lot lighter than oxygen. You know, the oxygen's a lot heavier. Won't that produce more pressure? No, no. At the same temperature, this is taking place at some temperature, whatever it is, doesn't matter. All the particles have the same kinetic energy. Same kinetic energy. Now, kinetic energy is a physics equation, but it has mass and velocity in it. And so the more massive particles like hydrogen are moving slower. They have less velocity. So the less massive particles like hydrogen are like Speedy Gonzales. They're all over the place. Ay caramba. So what I'm trying to say is, just because you're less massive doesn't mean you don't exert the same amount of pressure. You do, you're moving faster. So they all exert equal amounts of kinetic energy and therefore equal amounts of pressure. Now I have twice as many particles. That's going to produce twice the pressure. Back to that again. Okay, so I just have to say to myself, if I have 1, 2, 3 particles, and one of those 3 particles is oxygen, and 2 of those 3 particles is hydrogen, then hydrogen is exerting 2/3 of the total pressure. And the oxygen is exerting 1/3 of the total pressure. Do the math. 1/3 of 700 or 2/3 of 700. You can do it either way and subtract to get the other one, or you can multiply them both out and get the answers. So 2/3 of the total 700. So 2/3 of 700 gives me the hydrogen answer, and 1/3 of the 700 gives me the oxygen answer. And that's going to come out to be 466, 466. And the remainder, so you're going to take 466 and subtract it from 700 to get this one, or just multiply this by 1/3, either way, and you'll come out with 233. So this is 233, 466. Those are the pressures exerted by the individual gases.